to talk to you about solar analytics, the new version. A little bit about myself. 4 years ago, I joined Bloomberg as an intern. I was tasked with creating the first analytics component that we upstreamed back then, and now it's been in the solar releases since, I think, Solar 5. I joined full-time a year ago, and since then I've been working on the next version of solar analytics, and that's what I'm going to show you today. So, just a little bit about Bloomberg to start. At a large scale view, we are just an information company. We provide this information primarily to financial professionals through financial information and financial news. But in general, we just are a company that provides very fast and reliable data. In order to do this, we need lots of engineers. We have around 5,000 engineers that work primarily on creating high performance ingesting and retrieval of data. If you want to learn more about this and our core product, the terminal, which you can see at the bottom, please come and see us at our booth. So, let's get started on solar analytics. So, just to preface this, I'm really into baseball, so most of the examples I'm going to give are about baseball and baseball data. You don't really need to know very much about baseball to understand them. Just baseball is a lot. You can turn baseball into a set of data and then perform aggregations of that data. That's all you really need to know. So, let's say that I have a search index full of baseball data. I can search for that data through the search index and get back a list of results. These results don't really tell me how well a player has done over the course of, let's say, the last season or something. So in order to do that, to find out how good the player has been, we need to aggregate that data to provide valuable insight into it. And we can do this through analytics. As you can see in our example, we have a list of players. We really want to know, given this list of data, how well have they been playing? So, to do this, we use analytical expressions. Analytical expressions are just a combination of the data that you see in your search index. Two baseball examples are on-base percentage and batting average. These are two of the most popular ways of measuring how well a baseball player has done over the course of the season. And really, they can just be condensed down into a formula of fields in a search index, such as on-base percentage is walks plus singles plus doubles plus triples plus home runs divided by the amount of plate appearances that they've had. Batting average has a similar statistical expression. So, how do we actually calculate these expressions over our search results? So the analytics component you can think of as a kind of a mapping and reducing framework over the results you get back from your search index. So we can start off by querying for some Astros results over the last years. Astros is a baseball team. These are the players on that team. Given this list of results back, and as you can see, we're going to build up the expression on the right side of the screen, we can then combine the data together. First with mapping functions. The mapping functions let us combine data per document. So let's see how many times they got on base per plate appearance. So as you can see on the right side, we've mapped the addition function per document. And once the mapping has been done, obviously we go into the reduction phase. So reduction allows us to combine all of the mapping and field data over the entire result set. So we take the sum of the entire addition mapping function and the count of the plate appearances. Once the reduction has been done, we can perform additional mapping functions. And since we only have one reduction result per reduction function, we just map those two together, divide them, and find our overall on-base percentage of 600. So, how do we do this with other analytical expressions? So I have OVP on the left and average on the right. We'll just build them up like we did in the previous example. They both start off with just a list of fields that we want to use in our analytical expressions. Then we apply mapping functions such as adding all of the types of hits and subtracting plate appearances by the number of walks in the average example. Once the mapping has been done, then we can compute reductions over fields and mapping functions over fields. These reduce down into a single value, which then can be mapped into our overall result. So as you can see, it's not that hard to actually build up an analytical expression to really compute whatever you want. But it's not always really relevant to just take an entire search result and use all of that data in an analytical expression. For example, we don't really care about how all of the Astros did over the last year. We want to see which Astros did better than other Astros players. So we want to introduce facets into the system. For example, field facets, range facets, and query facets like Solar provides in the regular search. Let's just give an example of how this would work in analytics. We have field facets first. So you take a field that you want to facet over, group the sets of data by that field, and then perform analytics on each separate section of that data. It works very similar for range facets. You can do date ranges, or you group the data by given sets of ranges, as well as value ranges, such as innings. As you can see, not all of the data has to be represented in this facet, and that data is just ignored when calculating the results. We also have query facets, where you can give additional queries and group the data by that. So how does the mapping and reduction work when we introduce facets? Mapping, as you can imagine, really isn't affected. Since mapping is done on a per document basis, the facets don't matter, and so we can just map them for each document. However, reduction is affected because instead of needing to reduce all the data down into one value, we need to reduce the data down into one value per facet. So we're using a field facet on player, so we need to have one reduction for each player. Once the reduction is done, we can then use another mapping function to calculate the overall OPP. And instead of having just one value at the end, the mapping function would map each of the reduced values per facet value. So we get 3 values of on-base percentage back. Cool. So how is this really useful? At Bloomberg, we use this in a variety of ways. For example, we have a mergers and acquisitions function. So this gives the data on how big are the deals when companies buy other companies and that kind of thing. As this entire screen is powered by the analytics component in Solar. As you can see, we have a list of expressions, such as the number of deals, the minimum and maximum size of deals, and many more, as well as a lot of facets to group the data by and then calculate expressions over. If you want to know more about these use cases, come talk to us at our booth. We have lots of examples to show you. So the biggest problem with what I just explained to you was basically the version 1 of Solar Analytics. One of the biggest problems was that it did not support distributed collections, such as multi-sharded collections. So why is this a problem? Well, single sharded collections really can't hold vast amounts of data. The indexes are limited to 2 billion documents per shard, but really you can only use like a couple hundred of million documents stably in one shard. So if you want to compute analytics over more values than that, you need to split up your data into multiple shards in one collection. So the new version of analytics really needed to support distributed collections. Why is this a problem? Well, as you can see, mapping the data in our mapping and reducing kind of framework isn't affected because mapping is done on a per document basis, and documents are just like one document is on one shard. However, when you try to introduce reduction, this is when things get tricky, because instead of having one set of reductions at the end, you have one set of reductions for each shard that you have your data split into. So really, this is where the version 1 of the analytics kind of stopped because we didn't really know how to handle it. But now we need to kind of implement this, so how do we do it? Reduction of data isn't always hard. I mean, distributed reduction isn't always hard. There's a lot of functions such as sum, count, min, and max where you can just take the reduction over each shard and then apply the same function to each of those results. These are associative reduction functions, so these are the easy ones to compute. However, we support non-associative reduction functions such as percentile, median, and unique. These are not very easy to calculate distributedly, so we kind of need to allow each reduction function to manage its reduction across shards. Let's give some examples of this. So let's kind of assume we're trying to find the minimum of a date in the query that we get back, the unique set of players, the median of inning, and the sum of home run. Each of these functions will need different pieces of data sent across the shards to the originating node to kind of calculate the overall value. So min is an associative reduction function, so you can just send one piece of data from each shard, which is the minimum of each shard, and then take the minimum of those results. The sum is the same. You take the sum of each shard and take the sum of all of the results on each shard. Median, it gets a lot trickier. You need to send every piece of data from the shards to the originating shard, so you need to take all of the innings in each shard and combine them into an overall list, sort them, and then find the median at the end. And the unique set, you need to send the unique set of players from each shard to create an overall unique set and find the count of it in the originating shard. So the way we did it, each reduction function is in charge of exporting the data from the shard as well as merging it together in the originating shard. So this can get problematic with very large result size, because as you imagine, if you're trying to find the median over 1 billion values, it's very expensive to send 1 billion values over the network to the originating shard. Unfortunately, we can't really help this because to calculate a real median, you need all of the data there. However, what we can do is reduce the amount of data we're sending by saying that if we're sending the same data twice, if we need 2 sets of the same data, only send it once instead of sending it twice. For example, if I wanted to find the median of inning and the 20th and 60th percentile of inning, all of them would need a sorted list of inning to compute. So instead of sending the sorted list of inning 3 times, we can kind of optimize and only send the list once. How do we do this? We do this through reduction data sharing. So instead of reduction functions being in charge of sending data across shards, reduction functions reserve specific pieces of reduction data. For example, median and percentile would reserve a sorted list, and unique would reserve a unique set, and so on. The reduction data is now in charge of sending the data across shards, as well as merging it in the originating shard. So in this way, we can share data. So in the previous example, the median and 2 percentiles of inning would all just use one sorted list of inning to send across the nodes. I'll give a better example of this. So on the left, we have 5 functions that we're trying to compute. We're trying to compute the median of inning, the 20th percentile of inning, the 60th percentile of inning, the sum of home run, and the mean of home run. And below each of these functions is the pieces of reduction data that they are reserving. So the first 3 all need the sorted list of inning. The sum of home run obviously just needs the sum of home run, and the mean of home run needs a sum and a count of home run. So since we have 3 pieces of reduction data, we only need to collect 3 things in the shards. So we collect the data in the shards and combine them in the originating shard. So now we have 3 sets of reduction data that have been computed across the shards. And the reduction functions can now just look at this reduction data and use what they need. So mean of home run would take the count of home run, the sum of home run and divide it by the count of home run. The sum of home run would share with mean of home run and just use the sum of home run. And then median of inning, the 20th percentile of inning, and the 60th percentile of inning would all just look at the sorted list and find the piece of data that they need from it. So as you can see, we have 5 reduction functions that we're trying to compute, and we've been able to reduce the set of data we're sending across the shards into just 3 sets of data. This can drastically increase performance if you're trying to do non-associative reductions over very large result sets. So how does distributed request really work? The request comes into the originating node. The analytics component would then find 1 replica of each shard to send the request to, the distributed request to. The request is sent out to them, and then the reduction data is collected and then sent back to the originating component, where it is merged together and then computed. Then the overall results are computed and sent back in the response. Pretty straightforward. So, in general, distributed analytics lets you compute results over large result sets, but it also lets you speed up your aggregations a lot. So if you're trying to do associative reductions, you can see almost linear speed up with the number of shards you have, because you're distributing most of the computation to the shards and then doing minimal processing in the originating node. So if you have, let's say, 12 shards, you can see an almost 12 times speed up on some reduction functions. And obviously, the request interface looks the same no matter if you're using a single sharded cluster or a multi-sharded cluster. The non-associative reduction functions, such as median and unique, can use a lot of memory. For example, like if you're trying to calculate the median of 1 billion values, you're going to have to load all those billion values into the memory of the originating node. So it's nice to keep that in mind and make sure your performance isn't impacted too much. So what else have we included in the new analytics version? Basically, the biggest thing was supporting the multi-sharded collections, but we've also introduced advanced faceting, a lot of new mapping functionality in the in the analytical expressions, and then a new concept that we're calling variable functions. I'll go into these later. So, first off, backwards compatibility with the old version. The new version was designed to be almost fully backwards compatible with a few small exceptions. The analytics component no longer allows you to use the results of the expressions in defining query and range facets. This is mostly because if you need to have the results of these things, you have to talk back out to the shards and do more distributed things. So it's easier just to take it out for now. There's a couple of mapping functions that aren't supported that really weren't that useful, like reversing strings and that kind of stuff. The biggest thing is now that all fields used in the analytics component, except for like in query facet definitions, because you're just issuing another Solr query, must have doc values enabled. That's just how the component's been built so far. So back to the new things we've added in this version. Advanced faceting. So I've talked about field facets earlier, and I'm sure most of you all are very familiar with the concept. Value facets are very similar to field facets with additional features. Value facets allow you to facet on the value of a mapping expression. So a mapping expression could just be a field, and that would replace the the functionality of a field facet, but it also lets you do more advanced things. You can, like one example that we've got on the slide is doing a naive pivot faceting. So you can take the comma-separated values of field 1, the top value of field 2, and field 3, where all the missing values are filled with the string missing. You can then facet over this entire expression, and then basically just computing analytics results on each subgroup of the facet. There's an example here of an example defining a value facet. So you give it an expression, and then the sorting. The sorting is also much more complex in the new analytics version. You're allowed to give multiple sets of criteria. So you can say, I want to first sort by the expression price that I'm sending, and then I want to, if there's any prices that are the same, sort by the actual value of the facet that I'm computing. You can obviously give a limit and an offset as well, like in regular field facets. We've introduced native pivot faceting. So basically, if you're not familiar, pivot faceting is drilling down into multiple levels of facets. But much like we've replaced field facets with value facets, pivot faceting allows you to use mapping expressions instead of just fields. So the same capabilities that you're given in value facets, you're given in pivot faceting. Like value facets, you're also allowed to give complex sorting for each pivot that you have. The sorting for each pivot is independent, so you can do pretty complex things. I'll give you an example of a pivot facet definition. We have two pivots that we're trying to calculate. The first pivot is called category, where we're basically faceting over the category field, where if there's not a value, we're replacing it with no category. We have a sort criteria there. And then the second pivot is on location, which is the comma separated value of state and city. We also have a sort criteria for that. I'll give you an example of how the results would be calculated for this. So let's just take a result set and do this pivot facet that I just explained over it. So the first category that we see is electronics that have the following kind of set of results circled. We first calculate the analytics results for that result set, and then we find all of the children pivot facets for the electronics facet value. So we have two cities that these electronics are sold in, which is Austin and New York. Then we calculate the analytics results for those two sub sets of the data. We can have another category, which is kitchen, calculate the results for that, and as you can see, there can be overlap in the different facet buckets that we have. For kitchen, we also have children that we're calculating analytics results for, and then finally, we have a last category called no category. We calculate the analytics results for that, and then no category has no children, but that really doesn't matter. It's just no children are calculated for it. So that's the additional faceting that we've included. Now I'm going to go over the new mapping functionality that we've introduced in this component. So in the new component, mapping functions are allowed to have multi-valued fields. Originally, in the first version of the analytics, multi-valued fields were only allowed to be used in facet definitions. But now we've extended mapping functionality to use them too. So in general, the most mapping functions that the V1 of analytics had could be categorized as using a single value input and returning a single value, taking two single value inputs and returning a single value, or taking multiple single value inputs and returning a single value. And I'll explain how we've converted these into using multi-valued fields. So let's first start with a single value parameter and returning a single value. Two examples are log and negate. We can easily think of this as taking in a multi-value parameter and returning a multi-value. For example, basically you're just computing for each value of the input, take the function over that value and return it. So negation of strikes would work much like the negation of inning, where you're just negating each value of the field that or expression that you're putting in the parameter. Taking in two single value parameters and returning a single value is a little more complicated. We have a lot of these, such as subtract, power, add, so on. First, we can think of it as taking in a single value and a multi-value parameter and returning a multi-value. So for each value in the second parameter, we take that value and we apply it to the function with the first parameter. So subtracting inning by strikes, you take each value of strikes and subtract it by inning. And obviously, it works the same way when the parameters are switched. The last type is taking multiple single-valued parameters and returning a single value, such as concatenate, add, multiply, so on. You can easily think of this as taking in one multi-valued parameter and returning a single value, just using all of the values of that parameter as the values if they were a single value. So concatenating strikes, you would just take each value of strikes and concatenate it with a comma and so on. There's a lot of new mapping functions that we've added, as well as introducing the multi-valued fields. There's logical functions such as and, or, negate, so on. There's comparison functions such as equal, less than, or equal to, so on. And then really the cool new functions are the conditional ones. So we can have if statements in our analytical expressions now. So if this first Boolean expression, then choose between the next two expressions. We then have fill missing, remove, and filter. With this comes kind of a complex typing system as well that I haven't included in the slides, but they're very much documented in the SolarRef guide. So the last thing I'm going to talk about is variable functions. Variable functions are a new addition to the analytics component and basically allow you to embed your business logic into your request outside of your defining each of them for your expressions. So you can, in your request, define a function with parameters and then what that function should be mapped to in your expression. So for example, if the analytics function, component didn't provide a mean reduction, you could define it as a variable function of mean of A should be replaced by dividing the sum of A by the count of A. And then when when you're defining expressions, you can use it as if it was just a regular function provided by the analytics component. You can do more advanced things with the variable functions. So since the analytics component has functions that take in a variable length of parameters, variable functions should also allow this. So CSV of multiple, CSV should be able to take as many parameters as you would want to give it. And then we want to map that to a concatenate with a separator of comma of all those variables. So basically, the expressions that you give to the CSV function are just put into concat_sep with separated by commas. It's pretty straightforward. There's additional functionality for variable functions called Lambda Functions that are a little too complicated to go into right now, but if you're interested in them, please come talk to me at the booth. I'd love to talk about this stuff. So what y'all are probably asking is, how much speed up will I get if I switch to this new version of Solar Analytics? So we have given some performance values. So these are results of analytics requests with faceted non-associated functions, mostly just using unique over field facets, the unique function over field facets. We have 6 servers, each with 24 cores and so on. And so basically, each of the shards that you're seeing has 6 replicas. And the index size is roughly 400 million records. As you can see with the results, the original analytics component, the amount of time that it takes to query the data increases linearly with the amount of data that you're querying. However, with the new analytics component split over 12 shards, with your data split over 12 shards, you can see originally just faster query times, but as well, if you look at the rightmost column, you can see that as the data set grows, the speed of your query grows as well because you can process more documents in less time. So the analytics component scales the new version of the analytics component scales very well with larger result sizes over multiple shards. Cool. So, conclusions. Basically, the new analytics component allows you to calculate your results over larger result set sizes by parallelizing the computation and removing the limit over the amount of data that you can use. We have more advanced expressions with more advanced facets as well. I haven't mentioned this before, but we've also lowered the memory consumption of high cardinality facets, so facets that return hundreds of millions of results, making them feasible to use in production. We're now running this in production at scale with Bloomberg. basically with a lot of data and very fast query times. In general, all this is going to be available in the Solar 7.1 release, as well as the very detailed documentation of this component. But it is in the 7.0 release too, although the 7.1 version comes with a lot of bug fixes and it's a lot more stable. I would just warn you with that. The tickets below are the tickets on this new component. The original Analytics 2.0 ticket has been merged into 7.0 and approved, and then the remaining tickets are kind of waiting and to be merged into 7.1. Just wanted to give you all the timeline on this kind of stuff. Cool. Do you have any questions? Yes. So yeah, so that was something we were expecting. The stats component, we haven't done strict like comparisons performance-wise, but the functionality of the analytics component goes well beyond what the stats component provides. JSON Facets, I'm not that familiar with JSON Facets, so I can't answer that, I'm sorry. Yes.
For the non-reducible operators, did you consider approximate ones, like hyperlocal or stages?
Yeah, so yes, but we have a lot of functionality at Bloomberg that requires exact data. But hyperlog would be very easy to implement. So in general, the new analytics component is very pluggable, so you can, in a future release, we're trying to make it so you can add new functions through your schema, much like streaming expressions. Yeah. Yes. Yes. All of the results from the analytics component are exact. There's no approximations. Yes. Yes. So do you mean that like the users could be split across the shards into? Yeah. Mm-hmm. So yes, for faceting, the reduction is done on the shards as well. So you're doing for each facet value, you need a piece of reduction data. And so all of the reduction data is computed on the shards and merged in the analytics component. So when it's all sent back to the originating node, the component doesn't really care if it's a facet or an overall value. It's just combining all the results and computing actual values. So all of the like faceting and like grouping of data is done on the shard level, not on the actual initial component level. Hopefully that answered your question. Anything else? Yes. There's no shuffling done. So do you mean like getting all the reduction data back? Oh yeah, so it's, I just created so all of the data used in the analytics component uses like primitives whenever available, so I didn't really want to use Java bin. So I kind of created my own kind of streaming API just using like bits and like input streams with bits. It's as efficient as you could possibly be, I think. Yes. Can you speak up a little bit? No, no compression's done, but it would be very easy to add. So that's one of the things that we're kind of thinking about in the next kind of things that we want to implement. Is that it? Cool. Thank you everyone for coming. Hope you enjoyed it.
Thank you.